Here is Griffiths' Intro to Quantum Mechanics, and we're getting through most of the infinite square well problems. This is problem 2.8, where we have a particle inside an infinite square well. We'll draw it like that, going from 0 to A. And it has this initial state. So for time equal to 0, we start out looking like this. We can quickly sketch out a graph of that. So when x equals 0, everything's going to be 0. When x equals a, it's going to be 0 as well, because this inside the parentheses is going to be 0. And as you can see, if we quickly parse that out, what we get is a parabola. And we can even see where it's going to have its highest point. It's going to be at a halves. I can quickly throw in x equals a half. So then I have a minus a half. So I can write in here what my peak is right there, if I so want to. So this is its initial value, so it's like we put a particle with this initial state into the square well, and then as our particle exists in the square well, it's going to turn into our solution to the Schrodinger equation, which we had before, which is going to be the way that I draw it from 0 to A, which comes from this initial state too. We're going to have our general solution, which is still going to be the sine. So we still have this guy, and you can still use the same idea for k, that you know, it has to be equal to 0 at 0 and equal to 0 at a. So all the work that we did for our particles in the infinite square well still stands. That's just for all time not equal to 0. So this one started out as this shape, which is a parabola. And then as time progresses, it's going to turn into a sine wave. Now, first thing we want to do is normalize it. We can graph it, which I already did. I think it's a good thing to do to graph it, because once you graph it, you can visually see which stationary state does it most closely resemble. Well, that would be it's a parabola, but it looks a lot like our ground state, right? So it looks a lot like our, one antinode sine wave or two node sine wave. So what we would expect for n equal to 1. So I'm just going to use the solution we had before for our energy. What this is most resembling here, so this is where k equals n times pi over a, and then from our Schrodinger equation, since we have the second derivative of our function times our function equal to energy times our function. We get our K out squared, and that's where we get it out here. So this most resembles the case where n equals 1, or ground state. So our energy looks a lot like this state. Not perfectly, this is not a sine wave, this is a parabola. It's not quite the same, but that's what it most closely resembles. Now let's go ahead and normalize it. So we're going to have 1. So the probability of finding our particle in the well is 100%. And now we take our wave function, a minus x, and that whole thing squared. Or I should be strict and put in absolute values there. So what I get is I can pull out the a, capital A, and then we have dx, and I'm just going to go ahead and square this guy out here. So I have x squared, a minus x squared. We can go ahead and FOIL out that guy. So we have a squared from 0 to little a, and then I have x squared. We're going to FOIL this guy, so I get a squared minus 2ax plus x squared. And then of course you can parse that out. So these all become 3 very easy integrals. So I get, put bracket there, so I get a squared x squared plus, I guess that'd be minus 2ax cubed, and then plus from 0 to a dx, just x to the 4th. So those are all fairly straightforward integrals to do. As you can see, they're all going to give us the same units because we have our space dimension to the 4th, space dimension to the 4th, space dimension to the 4th. So I have my a squared out in front. My first integral, I have a squared here, and then x squared, that's going to give me x to the 3rd over 3. And now that would be from the limits from 0 to a, so I'm just going to go ahead and write that as a to the 3rd. Then I have minus 2a, and then we have x to the 4th over 4, so that's a to the 4th over 4. And then I have plus just the integral of x to the 4th, so that's x to the 5th over 5. Oops. So we can simplify that out, and we just get all a to the 5th. So that's minus 1/2. Which is good. We want to have certainly the same dimension. We don't want to have different units. And I'm going to go ahead and just use 30 as my common denominator. So I get a to the 5th over 30 minus 15 a to the 5th over 30 plus 6 a to the 5th over 30 So 10 minus 15 is -5. -5 plus 6 is just 1, which is rather convenient. Now what I have is a squared equals 30 over a to the 5th. So a is going to be the square root of 30. I can go and write this way, square root of a to the 5th. Or I could just write, and you could simplify out the square root of 30 too. But I'm just going to simplify the bottom. Because 30 is 3 times 2 times 5. No, you can't simplify it. Okay. So there's our normalization constant. That was square root of 30 over square root of a times a squared. All right, let's go on to part B now. Okay, so we have A. I'm going to go ahead and just write the results we got. Square root of 30 over a squared times square root of a. Or that could be a to the 3, or a to the, you could work that out, square root of a to the 5th if you like, however you like to put that. And then we had our estimate of the expectation value of the energy was just going to be our ground state energy. That's all that we estimate there. So we say that our estimate of our ground state energy is that. So that's what we're estimating we would get if we calculated out the expectation value of the Hamiltonian. We expect to get the energy state as it is outlined in Chapter 2 of Griffiths. Now we want to get the expectation value of position, momentum, and energy. And we're going to compare that to our estimate of the energy. Now we can't do our expectation value of momentum by taking the time derivative of the expectation value of the position anymore, because we're doing them all at t equals 0. So this is only at t equals 0 that we're considering. Okay, so our expectation value for our position, let's start there, is just going to be x times our psi value squared. Now we know what a is, so that'll be 30 over a to the 5th. And that's going to be x cubed. And I'm going to go ahead and just FOIL this guy out. Times all that guy. So basically we're going to have pretty much the same, because it's a very simple function, we have pretty much the same integrals, we're just raising them up a power of x. So if I multiply these all out so that I can get 3 very easy integrals, I have a squared times x cubed minus 2a dx, and that one's going to be, so there's our first one. All there's our second one, so that's going to be x to the fourth. And then our last one is just going to be dx x to the fifth. All of these are not bad. So we get a squared, and then we're going to get x to the fourth over 4 from 0 to a. And then minus 2 times a. That's going to be x to the fifth over 5. And then integral of x to the fifth is just x to the 6 over 6. And you see that they all have the same power, which is good. Because over here, my normalization constant has units of inverse meters to the fifth, 1 over meters to the fifth, and all of these have units of meters to the 6. So that means I can cancel all of these, a to the 6 with the a to the 5th, and I will just get units of meters, which is exactly what I want. In fact, I'm going to go ahead and just factor out that a as well. So that's going to be 1/4 minus 2/5 plus 1/6. And you can, by all means, just use a calculator here. I just do it the easy way and say multiply the first one by 30. Because if I'm doing something by hand, I generally don't bother in finding the lowest common denominator because I have a calculator, or I just do it's easy enough to do in my head. So now I'm going to do the second one times 6 times 4, which is 24. So I get negative 48 over 120, and then times 20 plus 20. So then that gives me negative 18. So 30 minus 48, negative 18, 20 minus 18 is 2. Um, 30 and 120, that's going to just turn into 1/4, so I get 2 over 4, or I get a halves. So my expectation value is a half, which is what you'd actually expect. If I graph this out again, you know that we had a parabola. That's not a good parabola. Let's pretend that's symmetric. It's symmetric about a half. So just as if we had a like no initial condition on our ground state, on our original energy, if we put a particle inside our well, we would have an expectation value of a half. We'd expect to find it in the middle of the well. Since this appears to closely resemble the ground state energy, it makes sense that we would get the same expectation value. And also, just looking at the symmetry of it, we'd expect it to be A halves. I can write that a little bit neater because the A kind of looks like a 9 there. There we go, A half. So that's nice. That one actually makes sense. Let's go ahead and get the expectation value for the momentum. If you forgot this formula, can write it out quickly. So for our momentum, we do have to take a derivative. So we're using our operator definition of momentum, which is h bar over I del x. So what I have is my a squared out in front, that guy, and then we're integrating over x, and then I'm going to have my psi at t equals 0, because we're only getting the expectation value at t equals 0. I have h bar over I, and then I have del x acting on this guy. So now we're getting into order does matter. So del x of, let's just multiply that through, of this equals, we have the derivative of xa is just going to be a, and the derivative of negative x squared is negative 2x. I suppose I could write that as full derivative inside there. Okay, I'm going to go ahead and pull out my h bar over I. I'm just going to call it, so I can put the I on top, I'm just going to call it negative I h bar. And now I have this guy, my psi, times the spatial derivative of my psi, which is this guy. So I have negative 30I h bar over a fifths. Now we're going to go ahead and parse this guy out. Save some space. I'm just going to go ahead and rewrite this guy here as ax minus x squared. I have a squared x minus 2ax squared minus ax squared plus 2x cubed. Now, these both have dimensions of meters squared, meters, and meters. So when I FOIL that out, everything should have dimensions of meters cubed. A squared x meters cubed, ax squared meters cubed, ax squared meters cubed, 2x cubed. So it's just meters cubed. So good. We all have the same there. Again, these are pretty easy integrals. I can go ahead and combine those middle terms, so that's just 3ax squared. So my first one, I get a squared x. My next integral, I have negative 3 ax squared plus 2, and this is just going to be x cubed. Very straightforward. Integrals, there should be not any issue there. So my integral of x is x squared over 2, evaluated at 0 and a, minus 3a, and then we have x cubed over 3, and then we have 2, and then the integral of x cubed is x to the 4th over 4. So let's simplify that out. We all have the same power there, which is very nice. And we do want to check on those units. Our units of momentum as just a quick reference should be h bar times inverse meters. So I have a to the 4th over 2 minus a to the 4th plus, oh, I should have written that as an a to the 4th over 2. And we close that. Let me make sure. We do not have a sign mistake, which I do not see one. Or actually I do. That should be a negative in there. I'm not sure where I made that mistake. But I made it somewhere. So this should be a negative. I'm not sure where I made the mistake, but I'm looking at my earlier notes and I have it this way. So I'm just going to trust my earlier self on that one. So those go ahead and cancel out. And what I get is 30 IH bar. My a to the 4th cancels with 4 of those over a. And I have units of, so h bar has units of joules, kilograms, meters squared over seconds squared times seconds over meters. So one of my seconds cancels, one of my meters cancels. I have units left over of kilograms times meters over seconds squared, which is momentum, mass times velocity. So there's our expectation value of our momentum. And now lastly, we're going to get our expectation value of our energy. And remember, we want to compare it to our estimate, which is that it looks like a parabola, a downward parabola. Looks a lot like half a wavelength of a sine wave. So that's what our estimate is. Let's see how close we are. So our expectation value of our Hamiltonian, our energy, which by the way, our Hamiltonian is just our kinetic energy plus our potential energy. Inside our potential well, we don't have any potential energy. The sides of the well are infinity. That's how our particle is bound. So our formula for this, I'll just write out the formula, is psi. And then we have our operator form of Hamiltonian. So in our operator form, it is negative h bar over 2m del x squared. So just like how you have coming from your kinetic energy being this guy, and then being 1/2 momentum squared over m, and then taking the operator form of your momentum, because our potential energy inside the well is 0. We don't have any potential energy inside the well. So that means you get 1 over 2m, and then your operator form was h bar over I squared, and then you have del x squared, which is all outlined in the chapter as well. So let's go ahead and parse that out for our case. We're going to have our normalization constant out in front here. We're only integrating from 0 to a. So we have dx. I'm just going to go ahead and push that multiplication through for my psi. I'm going to throw my negative sign out here. And then I have h bar squared over 2m. And then I have the second derivative of this guy. So we already know what our first derivative is. And I could write that as a full derivative. So, sorry, I did not. So we already got our first derivative. That was a minus 2x. So now our derivative of our derivative is going to be 0. And then we just have negative 2. We get a constant because we only had a polynomial of order 2. So if we take the slope of the slope, say you have some parabola, I take the slope, I get a straight line. I take the slope of that slope, I get a constant, which is exactly what I got. That's nice for us because that makes our integration a whole lot easier. So then I get a negative 2 out in front there. I'm going to go ahead and write out here. So I have negative 30 h bar squared, and then I have a, to the 5th, not squared, a to the 5th m, and then I had a 2 down here, and then this equaled 2, so those 2's canceled, making it even better. Now we just have this derivative to do, or this integral to do, which is pretty easy. So we could break that into 2 integrals. We get our first integral is just integral of ax. So that's going to be the integral of x is x squared over 2 minus our integral of x squared, which is x to the 3rd over 3. can see we got the same dimension, which is nice. Oh, I had a -2, so that went to a positive. -2, positive. So we have a to the 5th, and then that's going to be times 3 over 6 is 1/2, and then we have 2 over 6 is 1/3. Our a's cancel a little bit, so we get 30 h bar squared. 3 of those a's canceled, so that's over a squared m, and then that's 1/6. Uh, 30 divided by 6 is 5. And then we have m(a) squared. Let's write that a little bit neater. Okay, first check. Always, always, always first check. Units. Kilograms squared, meters to the 4th over seconds to the 4th times seconds squared. That's our h bar squared. Over kilograms, meters squared. 1 of our kilograms cancels. 2 of our seconds cancel. 2 of our meters cancel, leaving me with kilograms times meters squared over seconds squared, or a joule. Good. My expectation value of my energy most certainly needs to be a joule. So we got the right units, we're good. That's my expectation value of my energy. Now let's compare them, because this is fun. So I want to compare 5h bar squared to ma squared to my estimate was pi squared h bar squared to ma squared. So the question is, how does 5 compare to pi squared over 2? So 5 to 3.14 squared over 2. That's something that is about 9, a little bit more than 9, divided by 2, meaning that's somewhat close to 10 divided by 2, and is actually pretty close. I mean, if I put that into a calculator, I get 4.9. So actually very, very close to our estimate. And there we go. That is problem 2.8 for you. Never hurts to make sure you actually answered everything. Yep. So then you just compare it to that. Just as a quick reminder, the most common by far that I dock points for on tests and homeworks is not actually answering the question. So just as a friendly reminder, if you are in a class, read the question. You'd be surprised at how far that can get you in your grade.